Okay, so I just said this, but when we have energy released in a nuclear decay or any nuclear reaction, the energy can come out either as a photon. Generally, it comes out as the kinetic energy of the products, but sometimes it does come out as a photon as well. The amount of energy that's going to come out, or the amount of energy that we're talking about, is always written as Q, even though it's not always heat. But that Q goes back to some of our chapters on thermodynamics and thermal physics, where Q is energy that comes out. But it was rewritten Q before as heat, but here it's just energy. And it's the change in negative, the change in energy in our mass in our reaction times c squared. So number 48, and I'm going to do part of this, and I'm going to do number 17, probably all of that. But 48 is a little long, but we'll do some of it. So it says how much energy is released when a uranium-238 nucleus decays, emitting an alpha particle. And then it has us go through and wants us to do 4 more reactions, energy that comes out, where the first one is that the 238 releases a neutron, then releases a proton, then releases a neutron, then a proton, and it becomes successfully different reactions as it goes through this. And it also wants us to prove that this is essentially the difference between these energies that are coming out is the binding energy of an alpha particle, and it wants us to find the binding energy of an alpha particle as well. So I'm going to do part A, and I'm going to do part D. Maybe I'll do a little bit of B. We'll see. But let's look at A. So for part A, it says, what's the energy that's released when we have a 238? So let's actually write this out. We have a 238, and it becomes, we get an alpha particle out of this. So that means that we must make something which has 234 as its number here, right? And we could look at these actual so this is 92, and thorium is 90. So this is a typical alpha decay. So our initial mass is just this mass of the uranium-238. The final mass afterwards is the thorium mass plus the helium mass. If I add those together, I get... All right, so if I add these two masses together, I got this. And then if I take the mass of the uranium-238 and I subtract the mass, the final mass, I get 0.00456 U times c squared. All right, that's the energy that should come out. And this is going to be positive, so that means energy is coming out. I have less mass afterwards. So my Q is positive. I get the energy to come out. So if I multiply this by the 931,494,013, I get that 4.2476 MeV come out of every one of these reactions. For every single 238 that decays, this is the energy that comes out. I'm just going to do the reactions that happen for part B, and then you can sort of do the math yourself. But if they sit there and they say, okay, well, now we're going to say that instead of it doing this decay, we're going to have 238 decay, and it's going to release a neutron. So if it's going to release a neutron, then it's going to end up with something, it's still going to be uranium afterwards, right? It's still going to be uranium afterwards. It's going to have, we have 92 and we have 92, but it's going to have one less neutron in there. So it becomes this 237 instead. And so here, again, you'll have some initial mass and some final mass, and you want to figure out what the Q is. For the second part, now you're going to take this uranium-237, and it says that we're releasing a proton this time. So you're going to release a proton. You'll have to probably release some other stuff with that as well, for reaction-wise. But if you're going to release a proton, so this was 92, now you're going to have something which has got 91 protons So this is palladium. Is that what that is? And you still have 237. Oh, so now you've decreased your number of nucleons as well by one because it's over here as a proton. And so now you have this as your initial mass, the 237, and these two together are your final mass, where this is your proton, right? And so again, you'll do a Q m naught mf times c squared. And you'll go through and do two more reactions where now the palladium will produce something plus a neutron, and then whatever you're left with here will then release a proton. And for each step, you'll have an m naught and an mf. I do want to do the binding energy for the helium nucleus. So again, we're supposed to do Z times the mass of hydrogen, essentially N, which is A minus Z, times the mass of the neutron minus the mass of our helium times C squared. So this is 2 times 1.007825 U. This is 2 times 1.008665 U. Those are those values from above. And then I can go, and it tells me the mass of helium is 4.00260. Times C squared. So I add those all up. I get 0.03038 U times C squared. 4013. And I end up with 28.299, we'll just say, MeV. So this is a binding energy equation, and then also showing you how to do Qs that come out of a reaction. Let's look at number 17. It says a neutron has no charge, so there's no way to find its mass using a mass spectrometer. Right? Mass spectrometers work by the idea that you charge something up, and then you send it through a region where there's a constant magnetic field, right? We have a constant magnetic field, let's say in here, and if you have some particle, here he goes, and he comes in with some V, and he's got, say, some positive charge, then there'll be a V cross B, and you'd have, say, a force acting this way on it, right? If it was a positive charged particle, or the other way if it was a negatively charged particle. But if it's not charged, it's just going to run right through that magnetic field and not do anything at all. So what do? So the way you can figure out the mass of a neutron is have a neutron and a proton meet, and then they form, right? Because of the strong nuclear force, these two will form a deuteron. Basically, this is a heavy... This is this. You have a proton and a neutron, and they meet up and they produce this. They also have to produce a gamma ray. They have to do that for a couple of different reasons, but they have to do it also because there's now less energy in that hydrogen, in the deuterium, than there is in the proton and the neutron when they were free. And they tell us that this energy of this is, so the Q that comes out here is 2.2233 MeV. That's the energy that's coming out in this gamma ray. So if we look at this and we say, okay, well, the masses beforehand is the mass of the proton plus the mass of the neutron, and the mass after is just the mass of the deuterium. then Q should be equal to my initial mass minus my final mass times c squared. Writing in this, my initial mass is the mass of the proton, the mass of the neutron, minus the mass of the deuterium, which is my final mass, times c squared. I'm going to try to solve for the mass of the neutron before I plug anything in here. So I'm going to end up with Q over c squared is the mass of the proton, mass of the neutron, mass of the deuterium. And so my mass of my neutron is Q over c squared plus the mass of the deuterium minus the mass of the proton. Q is 2.2233 MeV over c squared. And the mass of the deuterium was 2.013553212U minus 1.007276467U. So this unit-wise looks very, very strange, but I'm going to remember that 1U is 931.494013 MeV. And so I'm going to figure out what fraction this is and get it in terms of U. All right, so what I did, just to be clear, is I took this 2.2233 and divided it by 931.494013 to determine how many U I have. I basically did a conversion. I said this many MeV per c squared is 1U. So this fraction, this is how many U I have. And so if I add these all up, plus 2.01355.321 minus 1.007276467, I end up with a mass for my neutron of 1.008664 roughly, which to the number of significant figures is exactly what the mass of the neutron is. All right, that's all I'm going to do for chapter 42. Hopefully that prepares you for what y'all need for the homework for that, and I'll do another video or two on chapter 43 next.